Okay, let's start. So today I will continue talking about how to approximate conductance. And just to recall, last time we have defined the generalized notion of conductance, which we call H expansion, which is nothing but like if you have a cut S, then the H expansion is the ratio of the cut size in original graph compared with the cut size in the graph edge. Here. Okay. So that is a edge expansion of a cut, and edge expansion of a graph. You're just minimizing overall cut. Okay, so now we were before talking about this. We have two ingredients that I was mentioning last time. Can someone tell me what is the first ingredient?
Every L1 metric is a cut.
Say it again.
Every L1 metric is a cut through.
Yeah, like Bourgain embedding. So any metric can be embedded into L1 with small distortion. And the second ingredient is about connection between what and what. Yes, please.
Just so I remember, is there a significant difference between like the edges and weights in GH, or like is there some sort of, or is it just kind of like whatever, like random?
I'm not sure I understand the question. Is there?
Yeah, like G and H are two different graphs, just sharing the same set of vertices. Is there any like pattern, I guess, to how they're different?
So they don't have to. There's no relationship between the H set of H and G at all. Think of G as a graph that you want to check the conductance, or you want to check the connectivity in G. And now H is kind of a graph that defines what it means to be connected. So for example, if H have only one edge between S and T, then H expansion is ST min cut. Right? Now we see that if H is defined to be something like a complete graph with some weight between edges, then if we set the weight correctly, then you measure, then that means H expansion is a conductance. So H is like to say what is the demand, what it means to be connected, to be well connected. And G is a graph that you want to estimate the connectivity.
Okay, so H is kind of like a cookie cutter example, like a simplified version of G almost. It's like easier to generate or something.
So in general, H can be any graph, really. But think of H as like, I'm not sure how to answer this. Let's take this offline. Yeah. I've come back to my question. What was the second ingredient? Anyone?
We can use the cut column to present any L1
Yeah.
metric.
Right. Any L1 metric is just a non-negative combination of a bunch of cut metrics. That is the second one. Yeah. So now we are ready to like we have everything we need, and you will see how we use it. So last time we see that this H expansion of a graph G can be written as some minimization problem overall cut matrix, right? And what we want to minimize is a ratio of basically the ratio of cut size in G and cut size in H. Yeah. Okay. And this problem is not clear how to minimize, how to optimize for. And the key idea is that instead of trying to minimize overall cut metric, we will try to minimize overall metric. So instead of cut metric here, it becomes just all metric here. That's a new problem, and we call this latent row relaxation. So LR, GH.
So ds or u comma v is just if it's passing between s and v minus s, it's 1 and it's equal to s. Is that it?
Say it again, sorry.
ds u comma v.
Mm-hmm.
Is it just the indicator function of dh is passing?
Right. Yeah, it's a cut metric. So yeah, ds dv is 1 if let's say it's 1. Okay. So so now this is a relaxation. So now, like, what is the point of looking at this relaxation? The point is that this relaxation, you can write it as an LP. And you will see why, but you will see how. But once you can write it as an LP, you can solve it, right? So that's one good thing about it. So let's see why we can write it as an LP. First of all, we have that this is just the minimization problem when what we want to minimize is a ratio. So let's normalize it. So let's say that we just assume first that the thing in the denominator is always 1. This we can always assume, right? And then it means what? It means that the problem here to compute LRGH is just to minimize the thing in the nominator overall metric D, and we have this constraint. But this is exact like what it means to optimize overall metric. Metric is just a function that obey triangle inequality and you have a symmetry and it's non-negative, right? That's the definition of metric. So we can just add this constraint. So this is just triangle inequality constraint, and this is non-negative constraint. And you know that you also the optimal solution, you will have that, this thing, we define it only for unordered pair, right? So that I don't need to write the symmetric constraint explicitly. Yeah. So I only need to write the triangle inequality one. So this is just an LP. Now we have an LP. So we can solve this LP and get this this number LR GH.
So the variables are the weights?
The variable, no, the weight is fixed. The weight of G is fixed. The weight of H is fixed. What we try to solve for is D. Yeah. We want to find a best metric, the best D. Like for every pair of U and V, you want to find the best D that obey this thing.
We also want to specify D of UV equal to D of VU, right?
So because I don't have I define D of D like the okay the variables here is just indexed by unordered pair. So I don't have like I have only DUV, not and I don't have DVU. So
Where it
in,
gives the variables.
yeah, so they are like they are the same like by removing one of the variable. Yeah. Okay. So now if we just compute the optimal value of this of the above LP, this is just the LRGH, right? So now we can compute this relaxation, and yeah, and obviously LRGH is at most H expansion of G, because this is a relaxation. We minimize our bigger set, right? Instead of cut metric, we minimize our alt metric. Okay, so that is just one side. But now we want to argue that, okay, this thing is not much smaller than the H expansion. That's the only thing we need to do. So what we will prove is that LR of H, okay, it can be a bit smaller than H expansion, but only by log n factor. So, and as I kind of say like last time, this log n factor shouldn't be too surprising now, because any metric is kind of close to a cut metric by the two ingredients that we have shown. The first one is that any metric is kind of captured by L1 metric with some small distortion log n. And L1 metric is also just a combination of a cut metric. So relaxing from cut metric to any metric, it's just kind of, you just off by log n factor. So let's try to make this formal, right? So, okay. You write, I want to prove this, remember? Okay. So let's start by just write LR of H. And let's say that we have solved the LP, and we get that the opt is the optimal metric from the LP that we just wrote above. So, and we can write LR of H is this. Yes?
So in that order of log n distortion, we only told if you are coming from cut metric to L1 metric, we have order of log n distortion.
Yeah.
But this one is not only over L1 matrix, right? We are doing on much more other matrices, right? Also, right?
No, between L1 and cut, there is no distortion. But between cut and L1, there is a log n distortion.
Between anything and L1? Between anything?
Yeah, right, sorry. Between anything and L1, yes.
Okay. So that is why this order of log n is also coming, because we are coming from anything to...
Right. So log n L1, and this is kind of the same. Yeah. And I should say combination. Yeah. All right. So we just write down the optimal solution of the LP, and we get this first inequality, equality. And now just by applying Bourgain embedding, we have this metric D opt. We can find a L1 embedding F such that F kind of approximate D opt nicely. So it's just the same with log n factor. So, and note that we know that F also is just a combination of cut metric. So for every UV, you can write this distance in L1 as a combination of distance in cut metric. Okay, so using these two things together, then we have this, right? So why? Because I mean, this thing is at least this, which is I just write it here. So maybe I should say this thing is at least this thing, and then this thing is just exactly this. So we have this. And about this, how about the guy below? So this is at most this. So, and then that's why I have log n here. Yeah. And so we get this. Okay. Question about this? That's fine, right? All right. And now let me just rewrite things a bit. So we have this sum. So what I will do is I just move the sum over S to here. Because I mean I just move the sum over S to like to the front. That's it. Okay. And now now what do we have? I replace the sum over S here by min. And that is true just because like if you have like two sum overall like from I to K, the above sum is summing over all AI, and the below one is the summing over all BI. This will be like at least you just minimize over all I. So exercise, but this is kind of believable, right? But you can try to prove it. So once you have this, what does it mean here now? This is now just the cut size of G when you fix S for each S in the collection SF. Recall that SF is just this collection of cuts. Once you given F, and you can create a collection of cut that capture F, right? So here it says that okay, minimizing over all the cut in this collection. And what do we minimizing over? This is just a cut size of G. Like this is exactly cut size of G over cut size of H, which is just the H expansion of the cut. Right? And this is just minimizing over this collection of cuts, but the H expansion of a graph is minimizing over all cut. So you have that this thing is at least this. So that proves it. That the relaxation, latent round relaxation, is not too small. Okay. So now we have this, which means that given like a graph G, if you want to estimate H expansion, just write down the LP, solve that LP, and then you can estimate it within log n factor. So by the way, this algorithm is not too fast, right? You need to resolve an LP. It seems not fast. not like the thing we want in this class that much. But this is, you will see like a fast algorithms later in class. By the way, I want to point out that besides solving LP and obtain this D-op thing, every other step is actually fast. You can try to think about this, but I will talk about this in the exercise session. Like once you have a D-opt, you can get like the optimal cut in nonlinear time, actually. So now want to talk a bit more about the limitation of what we just saw and what is beyond what we just saw. So the approach here gives you log-n approximation, and this approach will not be better than log-n, and you will see why is that the case in the homework. But there is a better approach actually. So there is another type of metric called negative type metric. It's a metric such that there is an f where you can write the distance function as L2 norm but square. That's when you call it negative type metric. Doesn't matter that much, but the point is that there is a version of Bourgain, something similar but better distortion. It says that if you have any negative type metric, then you can embed into L1, but now with square root log, a bit better. Now it turns out that if you try to write the H expansion and try to kind of follow the same approach we did in this class, but instead of relaxing the problem to all metric, write it down as relaxing the problem to all negative type metric. Then you can solve that too. But it will not be like it's not clear how to model it as an LP, but you can model it as SDP, which is a semi-definite program. So you can solve that and follow the same kind of argument. Then you get log-n, square root log-n approximation. Just want to mention this because that is like the problem of approximating expansion is kind of closely related to whether there is a good embedding or not. There is a survey about this in this paper. You can look at it. Also, so this is I'm talking here is about limitation on log-n approximation. Also, there is some other limitation. That is, what we are talking today is about, although like H expansion is a generalization of conductance, it's a notion which is about H expansion, not vertex expansion, and also in undirected graph, right? And it's not clear how to use this metric embedding approach to solve a vertex expansion problem or directed graph. So we will see later in class how to do that using a more robust framework called cut matching game. So that is for later class. But this is like a cool thing that I will really talk about it later. Okay, and this is just some exercise, but is for exercise session. And now I will continue with the proof of Bourgain. I skipped it last time. Now let's prove it, Bourgain. Just to recall, it says this, right? That is, given any metric D, you can find an embedding F that map any point into like just log square n dimension, such that the L1 distance between any 2 points after mapping log n approximate the original distance. So that is Bourgain. So, and we want to prove it now. And by the way, what I will try to prove is similar. It's just the same thing up to scaling. I will actually show an embedding, like how to construct embedding F, such that this thing is at least log n times the distance, and at most log n squared times the distance. But if you have this, then you just scale it by like something like log n, and you get this thing, right? A question about this?
Those two inequalities are different, right? So I did not get how you go from 2 to 1.
Sorry?
So how do you get from that inequality below to the above integral?
Oh, so let's see. If I divide, let's say this is f prime, okay? This is f prime. If I look at f prime over log square, then and call this thing f, then you will have this because of here, and you will have this because of here, right? So you scale it by log square. Okay. Now let me describe the algorithm. So this is very powerful tool, but it turns out the algorithm is just so simple. So first, let me define this thing. That is, we have a metric, right? And let's say that I fix some subset A in this X. And given any point X, I just define the distance from X to the set to be just the minimum distance from X to any point in A. So think like you have X here, and you have a point X, and you have a set A. Then d of XA is just a minimum guy, 1. Yeah. This is d of XA. And now the algorithm is this. So let's say that I have like I that runs from 1 to I max, which is something like log n or of log n. And also j that runs from 1 to log n. Okay. So now for each ij, I create a subset aij, such that aij is just a random set that I include each element in X with probability 1 over 2 to the j. So think like if j is like a big, if j is like if this is like a log n here, then it's like this set would contain something like one guy in one point in X. If this is if it's A I1, then you include everything with probability half. So, okay. So it just generates this random set, all of them independently. Okay. And now, given this, all of this log n square set, I can create a mapping now. That is, for each of the point x, I just write down the distance from x to aij. So f will have something like log n square coordinate, right? And for each of coordinate, this is just so d of f of x is just 1 up to I max, j max. Is it clear? The algorithm? Yeah, that's the algorithm. So can you tell me why? Let's say that if a graph is if a metric is defined by a graph G with m edges, why you can maybe you can try to think offline. Actually, the function f you can compute it in nonlinear time. But it's clear from the description that this can be computed in polynomial time for sure, right? How to compute it in nonlinear time? That's exercise. Now, what I need to prove is just that this f function is really like approximate the distance. So we want to prove this. And let's try to prove it there are just two things we need to prove, this and this one. So let me start by showing an upper bound. That is, we have this. The L1 distance is at most log n square times the original distance. So what do we need to do? So let's just write it down, really, right? The L1 distance is really just a sum overall coordinate ij, and it's just a distance, the distance in the line for each coordinate. That's a definition of L1. And for each of the coordinate here, let's just write this thing down. This is just by definition. All right. So because there are log n square indices of overall ij, if I can prove that dx to aj, the difference between dx aj and dy aj, if this difference is at most the original distance, then I would be done, right? Okay, so that's our goal. Yeah, because there are like just log n squared indices. So we would have this. So that's our goal. We would like to prove that this thing is at most the original distance. Now, but let's see why this is true. So actually, this is true for any subset A, not just Aij. So if you choose any subset A, dAx minus like the difference between dAx and dYA is at most the original distance. And this is just a kind of it's much easier to look at a picture and very intuitive. So you have point X here, you have point Y here, right? And you have a set A here. So let's see. This is the dxa, and this is dya, like the distance from the point to the set. All right. And what we want to show is that the difference between these two things is at most this thing. So this is kind of clear from the picture, but let's try to do it formally. So what I will do actually is that I will prove that the distance from X to A is at most this, from X to Y and Y to A. And and by the way, if the other thing is true as well, then this together would imply the claim, right? So let's try to prove this inequality. So distance from X to A. Let me define Y prime to be the point such that dya is the dy prime. So this point, the point in A that is closest to Y. Okay. And we have that, like, this thing is at most the green thing, for sure, right? And then by by triangle inequality, we have that the distance from X to Y prime is, like, to go from X to Y prime is at most this, to go from X to Y and then Y to Y prime. But d from Y to Y prime is just dya. So that's why d of xa is at most this. And that's why we have this inequality, which is just this thing. And to prove another way, it's just a symmetric argument. So now we have this. So each coordinate never exceed each coordinate in the mapping F never exceed the original distance and the log n square coordinate. So you get an upper bound. Now let's prove the lower bound. So we need some definition now. I would define a point and a ball and open ball. So let's start by this. You are given, suppose you have a point S and radius R. Then the ball from S of radius R is just, you include every point of distance from S at most R. And the open ball, okay, this is hypo. For open ball, you just make the same definition but with strict inequality. Okay. And now with this definition, we are kind of ready. So fix X and Y, right? We want to prove that for each X and Y, the L1 distance is not too small. So now let's fix X and Y. And And let me define, like for each j, let me define rj to be the minimum radius such that the ball around x, the ball, like the minimum radius r such that the ball around x and the ball around y is bigger than 2 to the j. So like, did I have picture? Yeah. So let's say that if this is, here it should be -1. So if this is like a r of j, rj minus 1 and rj minus 1 from x and y, then the ball of both of them is kind of bigger than this ball, and this ball is bigger than 2 to the j minus 1. That's just the definition. All right. And I would also define delta, the difference between r. Delta j is just the difference between rj and rj minus 1. Just how much, like, if you want to grow from like a 2 to the j size ball to the j minus 1 size ball to the j ball, how much do you need to grow? And note, by the way, that if I sum up this thing, delta, then the sum telescope, right? And you get rj max. So let me start with one assumption that rj max is not too big. So it's like a, it's smaller than the distance over 4. Meaning that if I define the ball R1, R2 here, R3, even if I go to like a Rj max, this is from X, then the ball around Y are still like these balls are still disjoint. That's all I want from this assumption. This assumption might not be true, but you will see that with just some small adjustment in the proof, then it would be fine. So let's just take this for now. Okay. Okay. So now let's say, yep.
The B of YR is a set of nodes, is it?
Yeah, set of points, yeah.
Points.
Right. So now let's say this. So let's look at any j, all right? And with the radius rj, we know that like one of them will have size exactly to the j, right? So let's assume that y is a smaller one, and maybe the ball of x is actually much bigger than 2 to the j. That's fine. But one of them will be exactly of size 2 to the j. Okay.
What is B naught and B? Both are different, right?
So BO is just an open ball. So it's just the same thing as ball, but I have strict inequality.
Okay.
Here I have strict, I have not like less than equal. Here this is just, so I just exclude the last one, guy. I just exclude the last point. Yeah. Okay. All right. So I look at Rj, and Rj is defined to be the first radius, minimum radius such that both balls are bigger than to the j. So let's assume that it's a ball around y is a smaller one. Is of size to the j.
I don't understand why you can assume there's a ball exactly as mass to the j.
Okay. So let's say perturb everything slightly, but yeah, that is true. So let's say that the one of them is smaller than not. Let's say that the ball around y is of size as more as the ball around x. Yeah, that can be assumed for sure, right? Yeah. But if you want to assume that it's of size exactly to the j, you can kind of, for every d yx, you can perturb it by epsilon, very small, and then with probability 1, then every distance will be distinct, right? But it doesn't matter. Small thing.
How can you assume R max to be how can you assume RJ max to be
It might not be true in general at all, but let's assume this for now. And
but the J max is log n, right? So the ball R bx R J max should include all the vertices, right?
yeah, so I mean there is a case where it is wrong, but I will just change the proof at the end and you will see that this assumption can be lifted. Yeah, so it can be wrong for sure.
Is this sort of saying like we're assuming for now that it doesn't grow too fast?
We just want that the last guy is not too big, really.
Yeah, so like every time maybe it's like grows by 1.1 instead of 2.
Yeah, I mean, I actually don't care how much it grows from 1 to j max. I just need that the last guy is not too big. Yeah. Okay. All right. So let's assume this. I mean, this can be assumed. And now, also we have that the ball around the open ball around y will have size less than to the j by definition as well. Okay. So in picture it would look like this. So if you look at the radius rj minus 1, then both balls here are bigger than 2 to the j minus 1. But if you go to the next radius, then for y at least, it's not too big. It's still like a 2 to the j, right? So now, I want to say this. I want to define some good event. I will say that Aij is good if Aij is disjoint from this ball. No, sorry. Contain some point in this ball. If Aij contains something here. But Aij is just disjoint from this. So it doesn't contain anything here. Okay. If this happened, then I say that Aij is good. Is definition clear? Like you have some ball here, which is quite big, and you want that Aij should contain at least one point in this ball. and you have this ball too. Although the radius is a bit bigger, it doesn't contain too many points. It's still to the j at most, and you want to avoid everything around ball of y. Okay. And you will see that Aij will be good with some probability, but let me explain the reason why we call it good. All right. Because if it is good, then actually it will contribute quite a lot to the L1 distance. It will contribute at least delta J. So why is that the case? This is because, you see, if it doesn't contain anything in ball of Y, then the distance from Y to A, Ij, is at least Rj. But it contains something inside this small ball. So distance from X to Aj is this. So the difference between these two distances is at least delta J. So that is basically, if you look at the coordinate Ij in the mapping, Aij contribute at least delta J. And we think of this as something big because why? Because suppose, for example, that somehow all of Aij are good. Suppose that is the case, right? What would we have? We would have that, let me just write down the definition of L1. It's just a summing over all Ij, the difference between the age, like distance from X and Y to Aj. And because Aij are good, then each of these coordinates contribute delta J. And they kind of, for each fixed I, if you sum over all delta J, they telescope to just R Rj max, right? And this is I max. And with good probability, I forget to say this, but let's say that Rj max is really like something like this. I didn't explain this. I mean, this will not be true, but if this is true, then we get this thing.
You can actually tell Rj max is greater than or equal to b of x, right?
It is what is like only with some probability it will be at least like a factor of the xy.
Rj max is defined as encompassing all vertices, right?
Say it again, sorry.
Rj max is the distance to the last vertex from y, right?
Last vertex from y.
What is Rj
Rj
max?
max? Rj max is just the distance, so that
All vertices are included.
yeah. So yeah, that's true.
To x should be smaller than.
Yeah, right. Yeah, if we assume that like Rj max is yeah, that's true. Thanks. Yeah. So it is clear from the definition that thanks, that Rj max actually is kind of greater than equal this thing. But I assume somehow that this is at most this thing. This will not be true, but we'll see why. Why we can adjust the proof and make it true. Okay. But if every set are good, then we are done. Now I want to just prove that like most of the set, like at least constant fraction of a set are good with high probability. Let's say half of them are good.
Can I ask a clarification question? Like, you said assume like the boundary, the number of vertices in Y with radius Rj is strictly less than 2 to the J. I was wondering like why is that always true?
Oh, because we assume Rj is just the first radius such that the closed ball of Y Rj is bigger than 2 to the J. So the open ball will have.
So you assume Y, the ball of Y is smaller than the ball of X.
Yeah. We assume by symmetry that is the case. Yeah. All right. So it's really enough to just say that like most of the set are good. All right. If all the set are good, we are done. And we want to prove that most set are good. Or at least half of them are good. So let's look at this first. Actually, each set, let's look at each set, Aij. They are good with constant probability. And this actually is kind of not hard to see. Really just look at this picture, right? So you have two sets. Like you have two sets. One set is quite big, something like 2 to the J, within factor of 2. One set is small, it's at most to the J decimal. And you want to, and now you pick up each point with probability something like 2 to the J, 1 over 2 to the J. So with constant probability, you get some point here. And with some constant probability, you will also avoid all the point here. Right? Like both set, like one set is bigger than 2 to the J within constant factor. One set is less than 2 to the J. And you sample with red, 1 over 2 to the J. So you get a big set once, and you avoid a small set completely. That can happen with constant probability. And this is just a calculation. And note that this calculation actually works because we this is where I assume that the balls are disjoint. So here I said that the set is good if these two events happen. I contain some point in the large set, and I avoid all point in the small set. But these two events are independent only if the balls are disjoint, right? This is why I assume that like Rj max is at most this thing, so that the balls are disjoint. But if they are disjoint, then you just need to compute the probability, the product of these two probability, and both of them are constant. Okay. Question about this?
So is it then it seeks.
Exactly. It will be just like that. Yeah. Yeah. So now we have that each set is good with constant probability. Yes.
Why are the two events are different?
Oh, because like you have two sets which are disjoint, and you ask about like, and each of the set here you ask about like whether like each point in AJ you sample it into AJ with independently first of all, right?
But if a point is in the closed ball of X, it's surely not in the open ball of Y, right? So the two events can be related.
One sec. The well, if I have point X and sorry, maybe call it A, and this point is B, whether I sample A or not, like even if I know if A is sample or not, it doesn't say anything about B. That's what I mean by like they are independent in this sense, and the two sets are disjoint. So even if I know about everything about whether each point in this set are sample or not, it's just completely independent whether any point in this set are sample or not.
Is the number of points we're going to sample is fixed or not?
No, the point is not fixed. The number of points that we will sample is not fixed. Aij is just really defined such that look at each point, sample that point into the set with probability 1 over to the j. Yeah. All right.
Yeah.
Yes.
I'm not sure if there is any typo on the ball flight. Some of them are RJ and some of them are RJ.
Oh.
I'm not really sure.
Yeah. Thanks. So this is okay. This is typo. That should be it, right? Yeah. Right. Thanks. Okay, so now each set is good with constant probability, and now so what does it mean? If we fix like for every j, the expected number of good set is something like I max over 100, because each of them is good with 1 over 100 probability. Okay. And now it's not hard to see that like if you have something like we can actually say that for every j, it's not just that the expected number of good set is at least I max over 100, but with very high probability, the number of good set shouldn't be like deviate from its expectation by more than factor of 2. That is, the total number of good set should be at least I max over 200 with very high probability. And this is true because like this will be true when you have something like log n. Like Chernoff bound can kick in when you have something like log n events. And if you have log n events, then and each of them kind of are independent, then thing will be close to its expectation with a very good concentration. Yeah. So this is application of Chernoff bound. So you can try to recall how to use Chernoff bound and convince yourself about this. But now we have that for every j, the good aij are like a constant fraction. So that's why we have that with very good probability. The L1 norm of this is at least something like this factor, like all of the I over 200, like constant fraction of all the I times this Rj max. And the calculation is the same, right? So you kind of, instead of summing over all ij, you're summing over all ij that such that the set is good. And for this good set, you get contribution at least delta j, which sum up to be Rj max. And you also have that for every I, like you have for every j, the good aij are constant fraction of all the I. So you have this. Okay. So how can we remove the assumption that Rj max is at most d xy over 4? I assume this, and it is not true in general at all. But we can just define, like, for every j, we define R prime j to be the maximum between Rj and this this threshold. Or you can just, like Chang-En said, you can really just consider consider all j until it grows beyond this threshold. All the j that go beyond that, you ignore them. But that, like, there might be some corner case where, like, all the j before the threshold is very small, and then for the last guy, now you intersect. So you still need, like, to just set it to be something like just set it to be like a minimum of this, maybe at the end still. Yeah. So now this is an exercise that you should try to look at this definition of R prime j and convince yourself that everything really just go through. Yeah. Any question about this conclusion? That for every fixed x and y with good probability, with very high probability actually, you get, like, the L1 distance is log n times the original distance. Yes.
I think the probability is small, but I think it's not the same with the probability I exercise 215. It should last a little bit.
I see.
Because Aij is the same for all x, y. It is not.
Oh, so this is like for just a fix. I just fix x and y. Yeah. Yeah, so Yahweh just mentioned that, okay, we have that this is true, but what if we just want to say that we want this to hold for all pair x and y? How would you deal with that? Can you?
Union bound.
Exactly, just union bound. Yeah. So we just argue about one pair now. If we wanted, like each pair basically fail with this probability, now you union bound over all pair. There are n square of them. So it's still good with 1 over n to the 8 for all pair now, for all. All right. So that is a proof. And that's Bourgain. And I think in the exercise session, I would tell you a bit more about like intuition. Like, can the proof be even simpler, actually? Do we need like all version of, like, why do we need all level of J here? Like, can we just sample one random point and define the distance to be the distance to that, like the mapping of x is just a distance to that random point. Would that work or not? So actually, because we still have some time, actually let's look at one example. Suppose that the graph is cycle, actually. So I talk about graph because we can always think of, like, I have a graph, I can define metric, right? So let me talk about graph, which is a cycle. And what if I just define a mapping which is very simple? I literally just choose a random point A. And I define, like, for every point X, I define the mapping to be, the distance to this random point A. Actually, this is good in cycle already. Because if you have any other point Y, it will turns out that the difference between distance between x to A and y to A actually will be something like original distance. So why is that the case? Right. So Jimmy, can you say again? Sorry.
Half the time you sample A from like the shortest path between x and y, and then if you take the average over sort of the longer path, it's close to x.
So let's say that maybe y is here. Yeah. And what do we have? We have that, let's say that this is like a,
Actually, I don't see that. What if x and y were like next to each other? Then like, your distance is just an expectation like annotation.
yeah. So let's see the proof.
So one more thing, the D is the shortest distance in the graph, or is it the?
Yeah, the D is now the distance in the graph. Yeah. So D is just this is a metric defined by a graph. So it's really the shortest, like the distance in the graph. Yeah. So let's look at this, right? Suppose that suppose that A, like, maybe it's good if I draw it in a symmetric way. So this is cycle, which, and this is X, this is Y, right? And let's say that, right. Observe this. If I sample A and it's kind of outside this bad region, then the difference between the distance to A will be kind of big enough within a constant factor. So let's look at, suppose A is here, right? Then the distance will be, the difference between the distance is what? It's like this thing minus this. So it's good. So like thing will be bad only when A is like kind of close to the center, and that's when the distance is like, when you look at the difference, then they really cancel out, right? If you kind of go out of the center just by maybe a constant factor of your distance, then you're good. And anything here is good. So you just need to kind of convince yourself that the red area is kind of always at most half of all the area. Yeah. So actually, if the graph is cycle, then if you just choose a random point and take the distance, like define the mapping to be the distance to that random point, then you're done already. Like at least in expectation is good. And how to make it a whole with high probability? You just random like log n points and look at the sum of them. Now using Chernoff bound, like the sum of this log n thing in total will be good with high probability. Like will be close to its expectation with high probability. So thing seems like a very simple, at least in cycle, but this simple idea is actually not good always, and we will see like why that is the case maybe tomorrow. Like this idea is bad in complete graph, and in complete graph you need maybe some other idea, but like you see how this idea can be developed and until like it seems that the proof of Bourgain is the simplest thing possible that works already. Yeah. So let's talk about this tomorrow. Yeah. See you.
Small question. So how does 5G from in the previous lecture now, how does it relate to 5G?
Oh, yeah. So if you set
In the previous
if you actually set it to be like this. Here. So if you set the weight in the graph H to be like this,
H is completely off, but it has these weights.
right?
Okay, I see.
Then it will be like they will approximate within like a factor of 2.
I see. So this string is right, but the lower bound for 5G from H is it has a log structure.
Yeah.
I see. Okay. This is unintuitive, right? That he is using this G, H thing.
Yeah. So.
Do you have any intuition?
Why is it a good thing to look at, you mean? Well, because, I mean, you can also write down the LP for the conductance and use the same approach completely.
Okay.
It's just that instead of writing but in the LP you will have this anyway, and I just feel that it's a bit easier to just write down like this. Yeah.
I see.
Yeah.
Okay. Thanks.
Sure.
Okay. So I signed up to describe the Bourgain theorem. Sure.
Okay.
When do you want the notes to be?
Anytime. Maybe in 2 weeks maybe.
Oh, okay.
Yeah. Thanks.
Okay. I'll see you tomorrow.
Yeah. Okay.
Professor, I'm wondering what's the motivation of H expansion?
So as you see that H expansion generalize the D expansion. And D expansion, as we kind of taught in the exercise session, even the expansion you can use it to measure how a set of nodes are well connected, right?
Yeah, but it's defined in 2 graphs, right?
Yeah. Is it, what do you mean?
Like there are a ratio between